Welcome back to the class of Calculus 3. We are in section 5.4 triple integrals. This is a triple integral. There are three integral signs, right? And accordingly, it is really evaluated as a triple iterated integral, which means you are going to evaluate three integrals, really. Okay, and also I suppose we understand actually this is a rather simple one because we are considering a triple integral over a rectangular box, but we still understand there are six ways, right? So in general, it's fair to say triple integral is more complicated than double integrals, or not to mention those single integrals. Okay. And the thing is, it is complicated, not just about the six different ways. And most of the time, we consider triple integral not necessarily over rectangular box. So we are going to have a little more discussion about the general region, or really can I say general solid, how the solid would look like. So this time we are considering a solid, it's in a very generalized fashion. Okay, imagine if you can look down the solid along the z-axis, and then you may want to know the solid, it is bounded a surface on the top and the surface on the bottom. Okay, and furthermore, really the projection from the top and the projection from the bottom, really they will have to match. Or really I'm saying, if you imagine if you are look down along the axis, the lower surface, it is totally blocked. It matches the same shape as the top surface. And then the projection, it turns out to be region in the xy plane. So in this case, the triple integral can be it would be more efficient if you evaluate the triple integral in this fashion. I'm trying to see if I think it's better to move this part of the text right underneath the graph. Okay, I'm trying to see if I can get it. I don't know if my computer is slow. It's not showing anything. It should work. Yeah. Okay, it works. That's all I want. Okay. In this case, as I'm saying, we could evaluate the triple integral by considering z first. Okay. And then essentially, after evaluating the integral in terms of z, we do have a function of two variables, right? X and y left. And then you can consider in the xy plane, you can consider the so-called type 1 or type 2 regions. And so a triple integral, it is reduced into a double integral by doing z first. And similarly, if you happen to have a general region or solid in the fashion such that if you can look the solid along the y direction, and then surface to the right would cover exactly the surface to the left. And then if that is the case, you can evaluate the triple integral by doing y first. Hopefully, if you look at the inner part, okay, by doing y first, and in the end, in this round, after this round, we're going to have integral in terms of x and z. And then you check into the situation into the xz plane, and hopefully you will see type 1 and the type 2, those things in the xz plane, and then you make the arrangement accordingly. Okay, doing dy first. And also it is possible, sometimes we do consider using the integral dx first. Okay, this is the case when if you could imagine you are seeing the solid along the x direction. Okay, from front to the bottom, from front to the back. Then the front and the back, really they should match the same shape. So which really allows you to evaluate the triple integral in terms of x first. And then we do have the region, the projected region into the YZ plane. Then in the YZ plane, you want to decide if you have type 1 or type 2, evaluate double integral accordingly. So this is in general what we consider how we evaluate a triple integral. We reduce into a double integral, and then double integral it is reduced into a regular integral. Then everything's done. Everything's done. Okay. So how about let's look at the next example. It is still from the textbook 5.38. 5.38. We are evaluating the triple integral over this function. And then the solid, it is tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Put in a simple way, a tetrahedron, it is solid such that all sides are triangles. I believe, yeah, it should be. Yeah, that is the tetrahedron. And also, don't overlook x equals 0, y equals 0, equals 0. You have to think very carefully. X equals 0 really would represent the entire YZ plane. Then y equals 0, it does represent the entire xz plane. Z equals 0, it is for the entire xy plane. And also, I hope it's a lot easier to recognize this plane here. It's a linear equation in the three-dimensional space, right? So that's a plane. And indeed, this is a plane rather easy to recognize because we do have all the intersections at 1. And indeed, if you look at the shape into the first octant, it is an equilateral triangle, right? Equilateral triangle. All three sides are the same. So this is how I see it. And then to evaluate this triple integral, if you think very carefully, you could look along from front to the back along the x-axis, or from right to left along the y-axis, or maybe simply you could look down from z-axis, from top to bottom. What you will see here is that in either case, we may have the surface, okay, let's say starting from these first, okay. Look down from the axis. The top surface, it is this triangle. The lower part, it is a triangle in the xy plane, okay. And then what we can consider here is that we can evaluate this triple integral in terms of z first, and then we consider region included in the xy plane. This is the region in the xy plane. But anyway, when we do z first, the function it is 5x minus 3y. In terms of z is a constant, and the lower bound of z is 0. Lower bound of z, the entire plane for xy plane is for z equals 0. So we have integral after evaluating in terms of z first. We may have integral like just that without z's. I mean this is a double integral with x and y only. And then for x and y, we consider region in the xy plane, which is this part of a triangle. And you can consider this as type 1, or indeed a type 2 would work too. I believe I follow the textbook. We are considering this as a type 1. So y is changing from 0 at the lower bound to the upper bound of the line, which is 1 minus x. So we are doing y first, and then we integrate in terms of x. And then eventually we're supposed to get a number. But anyway, I thought I skipped some number here. Hopefully you will say you can handle the calculation by yourself. And in the end, we figured out the triple integral, it turned out to be 1/12. And it is also worth to mention, in general, for any triple integral, there are 6 ways to evaluate it. Okay, and not only for a rectangular box, for this tetrahedron, really there are 6 ways. And to save time, I'm not going to go through all the details for all 6 ways. But anyway, I still want you to take a look. If I ask you, maybe don't necessarily want to ask you to do the actual calculation. I could ask you to set up the integral in 6 different ways, or maybe 3 ways, or at least in one more other way. Okay, so give it a try if you really understand the actual meaning of a triple integral. Thank you for watching.